So let's talk about section 4.2, the addition rule for probability. And that's literally all we're going to learn in this video is the addition rules. Now there is more than one addition rule. So the first thing is understand some of the probability properties. Anything that you have for probability, all of the probabilities should be between 0 and 1. Okay, if you have any probability that's more than 1, then that is not a true probability. So remember that. Also, the sample space, if you are looking for the probability of the sample space, so the probability that every event is going to occur is always going to be 1, and the probability for an empty set, so a probability that nothing actually occurs, is 0. Now, complement are one of the things that is really helpful when dealing with probability because sometimes it's easier to find the complement than it is to find the actual probability of something. So a complement is basically all the outcomes that are not actually in the event, whatever it might be. So to look at this instead, let's look and find the complement of the following items. So choose a red card out of a standard deck of cards. Well, the complement, when you think about it, is going to be the opposite of that. Okay, out of 31 students in your statistics class, 15 are out sick with the flu. Okay, and our last one is going to be in your area, 91% of phone customers use Phone South. Now, again, the complement should address basically what is not being in that event. Okay, and you kind of want to use words to describe these. So in our set of a deck of cards has 26 red and 26 black. Okay, if you're not familiar with a deck of cards, go get yourself a deck of cards or look at the pictures on the computers of decks of cards. You should become very familiar with them because they are going to show up quite a bit in this class. Okay, so we know that when we're looking at them, you've got some red cards, some black cards. So the complement is, remember, I'm asking you about choosing a red card. Well, the complement, well, what's not red? Black. So I can say the complement is choosing not a red card, but a lot of times I'm not going to say not a red card. I would just say choose a black card. Okay, our 15 students that are out with the flu, the complement will be basically choosing somebody that's not one of the 15 students out with the flu, which would be the other students. So the 16 students who are not sick is my complement. Okay, and remember our last one is that we had 91% of people use this Phone South customers, right? So since the event contained all the Phone South customers, meaning that 91%, everyone who is not a Phone South customer is in the complement. Okay, so thus the complement contains that other 9% of the phone customers in your area. Okay, so now that we kind of talked about the complement a little bit, the reason why we need to make sure we understand that complement is because any probability of an event plus the probability of the event's complement should always equal 1. This is called the complement rule, and it's a great way for us to find probability. Sometimes, for some problems, the probability of the complement is a heck of a lot easier than actually calculating out the probability of the event. Okay? So, and in those cases, remember, we know the probability of any event plus the probability of the complement of the event should always add to be 1. So therefore, the probability of our event is going to be 1 minus the probability of the complement. And that's literally me just doing a little bit of math there. Okay, so all I did was just basically, instead of it being probability of E plus the probability, here, I'll write it in. So instead of it just being our probability of E plus the probability of our complement of E equals 1. If it's addition on one side of the equal sign, it becomes subtraction on the other. But remember, this is function notation, so that whole thing goes together. And again, this is one big item, okay? So that's like one number, but we're using function notation here. So if you're worried that there is a 35% chance that you will fail your upcoming test, what is the probability that you will pass the test? Okay. Think about the wording on that. That's very interesting. Okay. If there is a 5% chance that none of the items on the scratch-off lottery ticket will be winners, what is the probability that at least one of the scratch-off items will win? Okay. So look at what you have and look at kind of what they're giving you. And that's kind of the biggest thing. So if you are worried that there is a 35% chance that you're going to fail, what is the probability that you'll pass? Okay. So pretty much the complement to the outcome of failing is passing, right? So pretty much since we know that it's 35% chance of failing, the complement will be the other part of that. So 1 minus our 35%. But remember, we don't ever deal with it in terms of our percentage. We like to change it to decimals, and then from there, we actually will get our decimal answer. Okay, and you're going to have decimal answers as well as sometimes having to convert them into percentages. So 1 minus the probability of failing, and the probability of failing was 35%, which is 0.35. Subtract that out, which is going to give you 0.65. So the probability of passing is 65%. So good news is that there's basically more than a 50% chance of passing the test. Now, the other one we talked about, the complement of having none of something is basically having at least one of it. And that's really important to notice the wording there. So the probability of having none, so having none, the complement is having at least one thing. Okay? So our probability of at least one winner is going to be 1 minus the probability of no winners whatsoever. Okay? And the probability of no winners was 5%. So 1 minus that 5% is going to give me that 95%, or also known as 0.95. So there's a 95% chance of having at least one winning scratch-off item. Well, how do we use this? Well, let's think about it in terms of something that's not necessarily as wordy. Let's look at it in sense of like, I don't know what the probability of something is to begin with. So roll a pair of standard 6-sided dice, okay, a pair meaning 2. What is the probability that neither die is a 3? So I want to know the probability that neither die is a 3. So let's think about this. Now, we can come up with all the different outcomes of every combination of the die that does not have a 3. Now, but remember, there are 36 different ways when you take 2 die together and putting them together. 36 different ways. Well, wouldn't it just be easier to find out, well, how many of them actually have a 3? And then basically the probability is going to be the complement of that. So if we just find what is the probability of getting a 3 and subtract that from 1, then you're going to have the probability of the complement of basically neither die has a 3. So let's list those outcomes. So we can get a 3 and a 1, a 3 and a 2, a 3 and a 3, a 3 and a 4, a 3 and a 5, a 3 and a 6. And then you've got a 1 and a 3, a 2 and a 3. Now the 3 and the 3 is going to be repeated here. A 4 and a 3, a 5 and a 3, and a 6 and a 3. Now remember, again, these are not necessarily the same. These are two very separate items, because think of it as like one's a red die, the other one's a blue die. Okay? They're not necessarily the same. There are 11 outcomes where at least one of those dice is 3. So because of that, and there's 36 different ways that we know when we're rolling a pair of die, and we learned that from 4.1, okay, we basically know that the probability of our complement is going to be 11 out of 36. Okay, and this is just me using my basic probability rolls. So now that I know the probability of the complement, I can basically use that and subtract it from 1. So the probability of my event is going to be 1 minus the probability of my complement. Okay, so we've got 1 minus 11 over 36, which is going to give me 25 over 36, meaning that my final answer is basically about 69.44%. Okay, and again, it's about, and notice I am using that squiggly equal, meaning that is rounded at that point. Okay, you can always use the fraction, which is basically the unrounded answer. So there's therefore, you know, the probability that neither die is a 3 is about 69.44%. Now, along with that, there is also the addition rules. Now, with the addition rules, this is taking into account our and our or. So if you do not know what and or are, you might want to go back and review that, because those are two items that you probably learned somewhere along the way, but a lot of people forget. And I like to think of it as you learned with sets and basic set notations that if you have A union B, that's basically the same thing as if you say set A or set B. So it's found in one or the other. The other one is basically if you have A intersect B. An intersect basically means they have to share something in common, which is going to be A and B. So what exactly do they have in common only? Okay, so the two events E and F, the probability of E or F occurring is given by the following formula. So the probability that E or F occurs is equal to the probability of E plus the probability of F minus the probability of E and F happening. Okay, so let's take a look at this. Circe is looking for a new condo to rent. Circe's realtor has provided her with the following list of amenities for 17 available properties. Now, the amenities contain the following. Close to the subway has 6 properties. Low maintenance has 7 properties. Green space has 5 properties, and 2 properties are newly renovated. Now, close to the subway and low maintenance is 2. Green space and newly renovated is 1. So if Circe's realtor selects the first condo they visit at random, what is the probability that the property is either close to a subway or has low maintenance? Now, this is where, again, I want to kind of go back and review just one or two things again. How many properties are there total? There's 17 properties. But remember, some of these properties can have multiple amenities. So if you start adding up 6 plus 7 plus 5 plus 2, you'll notice that you're going to get above 17 very quickly. Okay, so that doesn't really help me out. What's going to help me out is that I know that some of these have stuff in common. So close to the subway and low maintenance, there was 2 of those, and green space and newly renovated, there was 1 of those. But the question is I want to know that it's close to the subway or has low maintenance. Okay, keywords there, and or, always be on the lookout for them. So before we calculate the probability, let's verify basically Circe's realtor has an accurate count on the total number of properties. And again, we saw that at first glance, it seems that there's more than 17, but there's really not. Okay, so when you start adding them up, that's why it says that there's 20. But you have to remember that there's a couple of properties that had that multiple count. So there was 2 that shared some characteristics. There was 1 that shared another characteristics. So when you start taking that, in fact, there's actually 17. So 20 minus that 3 gives us those 17 if you take away the ones that are being double counted. So to calculate Circe's probability, the key word there was or, and really, again, once you see that word or, you kind of want to look and think of your probability rule. Now, remember the probability rule for addition basically says if I have the probability of E or F, that is going to be the probability of event E by itself plus the probability of event F by itself minus that double count of the probability of E and F both occurring. Okay, so E and F are just generalized for the 2 different events that can be. Now, most of the time, these 2 different events do have a lot more words involved on them, okay? So let's take a look at this with the words. So the probability of being close to the subway or a low fee. Now, we know there was 17 properties total, so the probability of being close to the subway was 6 out of 17. The probability of getting a low fee, well, there was 7 out of the 17 that had a low fee. But There was 2 that were close to the subway and had a low fee. So I have to subtract those out because technically these are being counted in this and this. So that's why I got to take away the double count. Okay, so I'm going to take away that double count, leaving me with 11 over 17. So approximately, therefore, the first condo that Cersei sees is either close to the subway or low maintenance fee is approximately 64.71%. Okay, now this is just using words. Understand that this can also go with tables too. So suppose that after a vote in the U.S. Senate on a proposed health bill, the following table shows the breakdown of the votes by party. Now, the votes on the health care bill, 23 Democrats voted in favor, 21 were against, 43 Republicans were in favor, 7 were against, 2 were independent for in favor, and 4 were against it. Now, if the lobbyist stops a random senator after the vote, what is the probability that this senator will either be a Republican or voted against the bill? Okay, again, noticing kind of in the question itself, that's the part where you have to pay attention to. They're going to be a Republican or have voted against the bill. So these are the people that have voted against the bill. These are the Republicans. And when you start to look there, as you saw, you can kind of notice I've actually circled 7 twice. I've circled it in the voting for the Republicans, or sorry, voting against, and also in the Republican part. So since that's being double counted, that's where that and is going to be. And is going to be where does that Republicans and voted against at the same time. Okay. So again, keywords, got to look for them, and or are going to be those major words that you want to look for in a lot of these word problems. Okay, so there's a total of 100 senators, all of whom have voted on this bill. Okay, and it didn't say in the problem, so just in case if you're a little unsure how I got 100, you can actually vote, add all these up, and you should get 100 total. Okay, but also by our knowledge of the U.S. Senate has 100 senators. So just in case if you're a little unsure where that 100 came from. Okay, all of whom voted on this bill according to our table. And basically, of these, 43 plus 7 of them are Republicans, and 21 plus 7 plus 4 voted against it. However, again, 7 of them are the both and. So using our addition rule basically allows me to say, okay, well, the probability of a Republican or against the bill is going to be 50 over 100 for our probability of Republicans, plus 32 over 100 for our probability of being against the bill, minus that double count of 7 over 100. That's being counted twice in this grouping, which is 3/4. So I have about a 75% chance that this lobbyist is going to stop either a Republican or somebody that voted against the bill. Okay, so let's go back to that rolling a die. So what's the probability? We're going to roll the pair of die, so 2 die. And again, we're just going to assume this is a 6-sided die. Unless otherwise noted, it's a 6-sided die. What is the probability of rolling either a total less than 4? Okay, again, keywords, always look for these keywords. They're really important to follow them. So what is the probability of rolling either a total less than 4 or a total equal to 10? Okay. So again, or, very important to note. That tells me that I'm probably going to be using the addition rule. Okay? And when we look at that, remember, it's probability of total less than 4 or equal to 10. Okay? So I need to figure out, well, what's the probability of getting a number less than 4? What's the probability, a total less than 4? What's the probability of actually getting a total that's equal to 10? And then I need to subtract, is there any of them that have both? Okay, so numbers less than 4 will be 2 and 3. So the only combinations of looking at a pair of die for 2 is snake eyes, so 1 and 1. 3 is going to be a 1 and a 2, or 8, 2, and a 1. Okay, now our total for 10, well, we've got a 4 and then a 6, okay? and then we've got the vice versa of that, and then we've got 5 and 5. So there's 3 different things here and 3 different things here. But remember, all outcomes of rolling a pair of die, just from the basic, if I roll a pair of die, how many different outcomes are there to begin with is 36. Okay? Now, here's the thing that you want to know. Remember the and. So by counting all the different outcomes, we can see that there was 3 for the totals less than 4. We also see that there's 3 exactly for 10. However, there's no outcomes that are both less than 10 and, or sorry, less than 4 and equal to 10. Like it just doesn't happen. Look back. Can you see any of these where it totals to be less than 4 but equal to 10 at the same time? It's not mathematically possible. So my and on this one is going to be 0. So hence our probabilities are as follows. So we've got 3 out of 36 plus 3 out of 36 minus 0 out of 36, because this right here, there was not even a possibility of getting that, which gives me 6 out of 36. And again, all fractions should be fully simplified, so you should get 1 out of 6. Now, speaking of that 0 is actually really important for us to know. So when you have an event like that, where 2 events, they have no outcomes in common whatsoever, this is actually called mutually exclusive. So the addition rule for probability for something that's mutually exclusive is basically the exact same rule, except for at this point, instead of subtracting the probability of E and F, this is 0. So because that whole thing goes to 0, and this is only if these events are mutually exclusive. So if there is that possibility there, then ladies and gentlemen, you're just left with this pretty formula here. So do you really have to memorize both formulas? Not exactly. So I actually prefer to remember the other one and then just remind myself that mutually exclusive events mean that and occurrence is 0. So how would this come out? So Caleb is very excited that it's finally time to purchase his first new car. Now, after much thought, he narrowed down his choices to 4. Now, because it has taken him so long to make up his mind, his friends have started to bet on which car he will choose. Okay, now they've given each car a probability based on how likely they think Caleb is going to choose that car. So Devin is betting that Caleb will choose either a Toyota or a Jeep, and we're going to find the probability that Devin is right. Now, they made these probabilities up, okay? So this is basically that subjective probability. But we can still use this to help us out here. So probability of getting a Toyota is 40%, a Honda 10%, a Ford 10%, a Jeep is 35%. Okay? And I want to know, again, that he will choose a Toyota or a Jeep, okay? So he has to only choose one car, right? Like, nowhere did it say he's allowed 2 cars, because he can only drive one at a time, right? So Caleb can only choose one of these cars. So these 2 events are, no matter what, are going to be mutually exclusive events. So because of that, we know that there's no chance of him getting a Toyota and a Jeep at the same time. That probability is going to become 0 because of the mutual events. And so because of that, we kind of shorten that formula. So we're going to assume that Caleb's firm have accurately determined Caleb's interest in each of the cars and that their probability predictions are good. So then basically the probability that Caleb choose either a Toyota or a Jeep is going to be the probability of a Toyota plus the probability of a Jeep individually there. Because again, you can't get a Toyota Jeep. There's no such thing as a Toyota Jeep, right? Or at least I don't know of one. There's not one that I know, that because these are 2 separate car companies. So there's no probability of this other last one here, which is going to be that 0. Okay, so when I add them together, we basically can figure out that Devin has a chance of 75% of correctly guessing what car Caleb is going to pick if he chooses between, he says, a Toyota or a Jeep. Okay, now guys, do remember when we think of mutually exclusive events, there are other ways. So you've got things like this where you have to kind of critically think, but there's some that also you should just know off the top of your head. So again, thinking back to your cards, what is the probability of getting a red club? Well, a club's black. So I can't get a red club. That's just not possible. So that would be a mutually exclusive event. Okay. Or what is the probability of drawing an ace and a face card? Okay. Well, an ace and face cards, there's no such thing as an ace face card. Like, it just doesn't exist. So that's another type of mutually exclusive event. So think of it that way. You really have to kind of think about, is there something that meets this, like Toyota Jeep? Like, is that actually possible? So think about them closely. If not, remember that you can always take that extra formula that's got the minus the probability of the Toyota and the Jeep, and just remind yourself that this is basically going to go to 0 and you're good. Okay. So let's try another one. So at a certain major event on an interstate, past experience tells us that the probabilities of a truck driver's refueling at each of the 5 possible gas stations is given by the following table below. Now we're going to assume that the truck drivers will refuel at only one of these gas stations. So thus making these mutually exclusive events, because you can't fill up at the BP and the Chevron at the same time. We're assuming they're only stopping one time. So what is the probability that the driver will refuel at a Shell, Exxon, or Chevron? Now, in this case here, I now have 3 events. So we had 2 earlier. Now we're adding in a third one. Okay, so one of the things that we want to kind of remember as we are looking for these here, please be aware that since there's 3 events, we basically, and we know they're mutually exclusive, we can just add that on. Okay, so basically it's going to be the probability of Shell or Exxon or Chevron. So plus, plus, plus. And again, they're all mutually exclusive, so we're just adding them all together, which is going to give us about a 75.39% chance. So again, I'm just literally taking these from the distribution table previously. So look at the distribution table previously. Okay. And again, notice I used the word distribution table. We just learned about those earlier. So again, very similar things that we've learned in previous chapters are kind of coming back. Okay. I do suggest, remember that when you are looking at these distribution tables, that do remember that they should always add to be 1 or less. Okay. So when in doubt, double check, because if this adds to be more than 1, it is not a true probability distribution table. Okay. Okay, and that's it. That's really all we have to do when we're looking at these, is just add them all together. Go back and review those formulas, so they're going to be very important to keep in mind, as well as remind yourself of the complement formula.